Welcome everyone. In this video we will derive Newton's law for gravitation, and the law is that the force of gravitation between two bodies is m1 times m2 divided by the distance between them squared times a constant, the gravitational field, the universal gravitation constant. This is Newton's law for gravitation, and we are going to derive this using Kepler's third law. Okay, so Kepler's third law states that it is an observation basically, and it is an observation that the radius of the motion of planets orbiting the sun, so the radius cubed, is proportional with the time of revolution, the period of the motion squared. This is, as I said, an observation by Kepler and another guy named Tycho Brahe, I think. Brahe, maybe. I might have spelled his name wrong, but Tycho Brahe was the guy who recorded all the data, and Kepler was his assistant as far as I know, and he looked at them and he organized them in such a way so that he was able to see that r cubed is proportional with t squared, okay? So at the time Newton wrote his book, the famous book, Principia, this was known. So he knew this, okay? And I'm not really sure if this is how he goes about proving his formula in the book, and I can, or you can, check it out, read through the book and see for yourself how Newton actually proved his formula, okay? And in fact, if you know how he arrived at this conclusion, please write that in the comment section. But today we will at least pretend that we are a contemporary of Newton and we didn't see his work, we only saw Kepler's work, and we're about to prove Newton's law before Newton. So it won't be called Newton's law anymore, it will be our law, okay? I'm just kidding. So the way we start is, we will say that the centripetal force will be the force of gravity. The force of gravity will provide the centripetal force. And what will the centripetal force be? It will be mass of a planet, which I will call mp, then the velocity squared over r, right? This is the centripetal acceleration. And when we multiply with m, we get the force. Oh, wait a minute. We just used that F net is equal to ma. That's Newton's second law. So we can't escape from Newton. He gets credit somehow, alright? We can't say that this isn't Newton's law. We are still using Newton's law. That's the reason, alright? He still gets credit. I'm sorry. So, for the force of gravity, now we're going to make a guess. We will say, okay, so this is an interaction between two masses. So what could it depend on? Well, it could depend on the masses, right? It could depend on the masses. It depends on the first mass, the mass of the planet, times the mass of the sun, let's say. It depends on both of them. And it should, intuitively, it should depend on the distance between the two objects, right? We can just feel that this would be right. And I know that this is not scientific enough, but we are really developing a theory, and there are leaps of faith at some point, okay? And at some point you take a leap of faith, you develop a model and just test it. Not everything arises from previous knowledge. Not everything is mathematical in science. That's what I'm trying to say. Some things come from observation, like Kepler's third law. And using that observation, you can prove another theory. Or you can use Newton's law to prove Kepler's law, okay? They are equivalent. One is not superior to another. So we have that. And as I said, it might depend on the distance between the two, r, but we don't really know which power of r it is. In fact, that is what we're trying to find. So let's say r to the nth power. And we want to find what n is. But when we look at this equation, we say, hey, this is not quite enough because the units would not match. We need a constant on the right side, which we just named with a capital G. Alright? You could have put any constant, but we will put G to be consistent with what Newton did. And also you might be saying, well, why should the masses be like that? Maybe one is squared, one is cubed. Well, in fact, you can't say that the powers are different because this is a symmetrical picture. They should have the same power, but you're right that maybe one is squared. Who knows? Only answer that we can say is when we test this with reality, when we apply this model to the data that we have already, this doesn't work out, okay? That's the only thing that I can say, honestly. So we start with this and we want to find n. What is n? Because when we find it, we are done. And it better turn out to be 2, because otherwise Newton made a huge mistake. And we also did, by not noticing the mistake for 400 years. But I don't really think that there will be a problem. So the mass of the planet cancels. Well, that's nice. And then, well, we could even cancel one r, I guess. Why not? So this goes, this is now r n minus 1. Okay, and then, well, what is v? V is going to be equal to, we can assume that the objects, the planets are moving in circular orbits. I know that's not correct. Kepler said that that is not correct. His first law was that the planets orbit the sun in ellipses. But if we take that the orbits are circles, which is not really a bad approximation, we get that the velocity will be, and since this is a uniform circular motion, the speed is constant. It is going to be the total circumference over the period. So it is 2 pi r over t. Cool. Now I will substitute that for v squared. So I get 4 pi squared r squared over t squared equaling g mass of the sun divided by r raised to the power of n minus 1. And then, well, let's see, what can I do? At this point, I will just take a step back and I will say, well, why don't I collect the r's on the same side? So I multiply by this factor on both sides to get 4 pi squared r, where that is 2 plus n minus 1. So r to the n plus 1 over t squared should equal g times ms. Now, if I divide both sides by 4 squared, and that might seem like an arbitrary choice, but in fact it is not. You will realize why that is the case. We have r raised to the power of n plus 1 divided by t squared equaling g ms divided by 4 pi squared. Cool. Now, what is the takeaway here? I want you to focus on the right side. Ms, that is the mass of the sun, that is constant. 4, that is a number, that is constant. Pi squared, even though it is irrational, it is a number, it is constant. And g, we said that it is a constant, right? We assigned it to be a constant, it is a constant. So the right side, this is a constant. Well, didn't we say that r cubed is proportional with t squared? That means that we could say r cubed is equal to some constant, let's say capital K times t squared, right? Right. This is what constant means. This is what proportional means. So it turns out that we have r to the power of n plus 1 divided by t squared equaling a constant, and we also know that r cubed divided by t squared should equal a constant. Then you can, I think, see that n plus 1 should be 3, because this is the power of r and 3 is also the power of r, which means that n is equal to 2, and just like we expected, we get that n is equal to 2. So don't worry, Newton did not do a mistake. He was right in his calculations, well, at least for classical mechanics, alright? Anyways, I hope this video was helpful. If you have any questions, please add them in the comment section. I hope to see you in another video. Until then, take care.